Hello and welcome back to question 3. Now in this video we're just going to do part 1. So in question 3 we're given a function and f is such that x gets mapped onto a over 2 minus x, where x belongs to a set of real numbers and x cannot be equal to 0 or 2. Now some of you might be thinking, oh, that is such a boring way to do mathematics. Why do you have all these kind of conventions that are so, stuffy, right? Okay, so let me very quickly just tell you what is actually going on and maybe a glimpse into why we do this kind of things. Okay, so to simplify things, first of all, let's not think about mapping. Let's think about a function f as a machine, right? It accepts an input and it gives an output. So if I have an input, say k, then the output will be f of k, right? So in this example, f of x is defined to be a over 2 minus x, which means that if I put in the input of k, right, then my f of k would just be 2 minus k, right? Every instance I see an x, I replace it with the actual input, which is k. That's it. You might already know this from secondary school. Now, let's look at what we're supposed to do, and that is in part 1, find out what is f squared. Now, f squared actually is f into f. Right, so that's f of x. So this is actually f of x. Okay, conceptually what's happening is you are actually taking one machine f, right, and then you put in a second machine f right at the output of the first machine, right? So you get f of x. So that's like f squared, applying f 2 times. So let's look at what's happening here. If I put in an input, say x, where x can be any number that we want to put in, then the output will be f of x from my first machine. Now this output from the first machine becomes the input of the second machine, right? And then the output of the final, of these 2 composite machines, so these are called composite functions, by the way, is f of x. Yeah, so that's what's happening over here. So let's look at this, how to do this. Yeah, so f of x, so let's write this down. F of x, oops, there's one too many f's. Okay, and you can sort of see that, hey, if f of x equals to this, I can also substitute this thing with a over 2 minus x. Okay, so my input is a over 2 minus x. So if my input is a over 2 minus x, then every time I see an instance of x, I'm going to replace it with my input. And that's it. This is f squared. But I don't want to express it in this form because there are fractions inside fractions, nested fractions, right? So let's express this in a nicer way where we multiply by 2 minus x to the numerator and denominator. That will give us 2a minus ax over 4 minus 2x minus a, right? And this is our f squared of x. Now to write it in the proper form, right, it will look like f squared is a machine, right? Actually, it's a composite machine. It's a machine that's made out of 2 machines, basically, right? F squared is such that your x gets mapped onto, meaning that if I put in the input x right at the top as my first input, the ultimate output I'm going to get is this. This is my ultimate output. Okay. Now what is missing is I need to write a bunch of stuff over here called the domain. Now why do we need to state the domain? Now to understand that, you have got to think about maybe like a specific example, like vending machines. Vending machines are an example of a function as well, right? If you put in coins, you can choose a drink and then the drink comes out. So the input is the coin, the output is the drink, right? So if everything works well, everyone's happy. But say if you try to be funny, you take some coin from another country, right? You stuff it into the vending machine and then it gets jammed. The machine spoils and nobody else can use it, right? So what the domain actually does is it tells you what kind of coins this machine accepts and what kind of coins the machine does not accept. That's what the domain does. It's an instruction to the user. Okay, so over here in this question, you can see that this function is defined with this, and it tells you that, hey, this machine accepts these coins, but it does not accept these coins. These coins will destroy the machine. Don't put those in. Okay, so now if I look at my f square, I need to determine what kind of values will destroy my f square, right? So first of all, maybe I want to look at this point here at the first input. What kind of values am I not allowed to put inside here? Luckily, the question has given that to us. You can put in all sorts of coins as long as they are real numbers, but just don't put in 0 and 2. So I'm going to write that down. Let me use orange. X belongs to the set of real numbers. X cannot be 0 or 2, or else my first machine would have broken down before it can even reach the second machine, right? So if that is fine, right, then it goes through to this part here, where we have another problem over here. Right here in my second machine, I cannot accept 0 and 2 again, which means I need to check whether any of these outputs from the first machine gives me 0 or 2. So let's do a quick check, maybe with a pencil. Let f of x equals to 0, and you find that this is not possible. As long as a is not 0, f of x will never be 0, right? So we're kind of safe there, right? This coin will not affect our second machine. But let's look at f of x equals to 2. Haha, this one actually there is an answer. Okay, if you simplify this, I think you get x equals to 2 minus a over 2. Right, so this is one of the possible values that passes through the first machine but will cause my second machine to jam up, because when it comes to the second machine, it becomes when it comes out of the first machine, the output is 2, which will jam up my second machine. Okay, so I'm going to include this as well, and you can kind of see that if I substitute 2 minus a over 2, right, you can see that this denominator goes to 0, and indeed it will destroy my second machine. So over here, this is the answer for f squared. We have given the expression of how the machine works, and then what kind of coins it accepts, what kind of coins it does not accept. Alright, now let's look at the second part of part 1, which is to find f inverse. So to find f inverse, let's think about again conceptually what's going on. To find f inverse, what is happening is it's kind of like this. Usually you have an input and you have an output, right? But let's say if one day I'm walking past the vending machine again, I see someone take out a can of Coca-Cola. Can I trace back and find out how much money this person put in? I could just look at the price chart, right? Oh, look, a Coke costs $1.10. This person must have put in $1.10 into the machine. So conceptually what is happening is I'm looking at the output, right? And I want to obtain what was the input that got there. Okay? So we have a special method for that, and that is we let f of x, right? So f of x, equals to a over 2 minus x, small x. I'm going to let f of x become big Y, and my small x becomes big X. Then I'm going to make big X the subject of the formula. 2 minus big X equals a over y. Big X equals to 2 minus a over y. And here, then I can say that f inverse of x, you know what, let's write it this way, will get mapped to 2 minus a over small x. Okay, so this is the method to get the inverse function. Now, what is the domain of f inverse? What kind of values can I not put into this machine f inverse? Okay, again, going back to the vending machine example, right? If I saw someone take a cucumber out of the vending machine, surely that's wrong, right? Because cucumbers don't come out of this vending machine. If I walk past and saw someone take a cucumber out of the vending machine, I will not be able to figure out what was the price that this person put in, because cucumber is not an item on the vending machine. So if you think carefully, the kind of things that I can figure out is the kind of things the vending machine can give out, or that's on the price list, right? So the domain of the inverse function is the range of the f function, the non-inverse function. Okay, so let's just write it down. The domain of f inverse is actually the range of f. And if you actually use a GC to plot out the range of f, you find that except for 0, right? Okay, x can be any real number, or rather the range can be any number. I set x equals to 0, and one more value. What is that one more value that we cannot get? And the clue comes from the coin you're not supposed to put in, right? You're not supposed to put in 0 and 2. Okay, if I put in 2, then this whole thing goes wrong, but if I put in 0, I'll get a over 2. So that's one of the values that you cannot get, a over 2. Okay, so that actually is the domain of our F inverse. So I can say that, hey, for F inverse, you can put in any kind of things you want, just don't put in 0 and a over 2, right? And that is the answer for F inverse. I hope you found this helpful, and I'll see you in the next video, question 3 part 2 and part 3.